Hello friends, and welcome to the course of Power Electronics in the Electrical is Easy channel. So in the previous video we have started with the construction of the power diodes, right? So as a recap, we have seen to have higher reverse breakdown voltage, a power diode has a third layer which is called a drift layer and it is very lightly doped, right? Now the reason of using the drift layer was to have higher breakdown voltage, right? To have higher breakdown voltage you have the drift layer. So what does the drift layer do? Because it is very lightly doped, it helps in the production of a wider depletion region, and naturally when you have a wider depletion region, you have a higher reverse breakdown voltage. So that was the concept that we have seen in the previous video. So let us continue our discussion and move to the reverse bias condition in the power diodes along with the drift region. Now we have already seen the reverse bias characteristics of the diodes, right? But now we will be introducing the drift region and we can see what all concepts we can learn from this particular topic. So the basic idea naturally in any kind of a diode is that in the reverse bias condition, a depletion layer is formed in the power diode. As in case of any diode, in the reverse bias condition, a depletion layer is formed. So the question here is, where is the depletion layer formed? So that is the question that we have to answer. So naturally you have seen that in the construction of the power diodes using the depletion region, you basically have a simple construction like this, right? So you are having a P plus layer which is highly doped, you are having an N minus layer which is called the drift layer, it is lightly doped, and then you are having an N plus layer, and here you are having the contacts. So this was a basic power diode construction. So the depletion layer is formed in the P plus and N minus layer. Naturally, any depletion layer is formed at the junction of the P and N regions. So here you can see the depletion layer will be formed in this particular area, that is between the P plus and the N minus layer. Now, since the P plus region is heavily doped, I have already told you the plus sign here indicates that it is heavily doped. So P region plus heavily doped. N plus region is heavily doped with the donor atoms, and for the P plus region naturally it will have acceptor atom and it will be heavily doped. In the drift region we already seen it is orders of magnitude less doping. So since P plus is heavily doped and the N minus region is very lightly doped, the depletion layer almost extends entirely into the drift region. That we have already seen in the two videos before, right? As the doping decreases, we have already seen this idea. We'll just write it here. As the doping level decreases, the depletion layer will move towards that region, right? So in this case, the P plus is heavily doped and the N minus is very lightly doped. So therefore, almost the entire depletion region will be in the N side of the diode. So if you see this particular structure here, what I am trying to say is that the depletion layer, I'll just change another color here. The depletion layer will be almost in this particular region where I am showing. The depletion layer will be in the N minus region because P plus is very heavily doped here. So depending upon the width of the drift layer. Now this drift layer, you know that it is a physical construction, right? There is a physical dimension for this width drift layer. So if you call the width of the drift layer as W drift is the width of the depletion layer. So this is the physical layer of that. So W drift is the physical width of the drift region. Now based on the physical width of the drift layer and the level of doping, you can have two conditions here. One condition is that the depletion layer will exist throughout the N minus region, right? When the depletion layer is forming, it depending upon the physical width, that is W drift, and the doping concentration, naturally the doping concentration will indicate how much this depletion layer is going to grow, right? So if you have less doping, you will have higher depletion region width, okay? And if you have lower doping, you will have less depletion region width. So depending upon the physical width of the drift layer and the level of doping, you are having a condition that the width of the drift layer can be either greater than or smaller than the depletion region width. Okay, so that is the basic idea. So you know that there is a depletion layer which is going to form. So based on the physical width of the drift layer and the level of doping, the width of the drift layer can be either greater than or smaller than the depletion region width. Okay, so for example, you are having your depletion layer only till this point here. Okay, so this is one condition. This is your W of the depletion region. I will use it like this. I will use this symbol. Okay, W of depletion region is only till here. For example, this is the W drift, right? This width is the width of the drift region. But sometimes what can happen in the other case, the width of the depletion region, okay, it can exist throughout the drift region. Width of the depletion region can exist throughout the drift region. Now based on this particular fact, there can be two types of diodes. So based on this classification, that is the width of the depletion layer and the width of the drift layer, you can have two types of diodes. One is called the punch through type and the other is called the non-punch through type. The name itself almost gives away what type of diodes we are going to deal with. So in a punch through type of a diode, the width of the drift region is smaller than the depletion layer width. Okay, that means the depletion layer is going to exist throughout the drift region. Okay, so in this case here, what is meaning? The W drift is less than or equal to, also we can tell, less than the depletion region width. I hope I am clear here. So as you can see in the definition, in a punch through type, the width of the drift region is smaller than the depletion layer width. Okay, so what does it mean? The depletion layer actually spans the entire drift region. See, the drift region is smaller than the depletion region, right? So naturally, what does it mean? The depletion layer spans the entire drift region and is in contact with the N minus layer. Okay, when we see in the drawing, it will be much more clear. So the second type is called the non-punch through type. Okay, so in this what happens? The width of the drift region is larger than the depletion layer width. That means the depletion layer is not going to span the entire region of the drift region. Okay, so in this, what is the condition? The depletion layer boundary, okay, does not reach till the end of the drift region. So naturally, non-punch through type means the depletion layer boundary does not reach the end of the drift region. Whereas in a punch through type, naturally the name itself is telling punch through. In a punch through type, the depletion layer spans the entire drift region and is in contact with the N plus region. So if you see two diodes here, I am having two diodes here. So let us call this as diode 1, okay, and let us call this as diode 2. So this diode D1 is your punch through type. Okay, let us take it as punch through type. So diode D2 is your non-punch through type. So since this is a punch through type of a diode, okay, it has a higher width, higher depletion region width. To have a wider region of depletion region, higher depletion region, the doping concentration of this N minus layer must be naturally less than the doping concentration of the non-punch through type. Okay, so for example, let us take this punch through has doping concentration of, let us take it as NDD1. Okay, it is this value. And for non-punch through type, let us take that it has a value of NDD2. Okay, so since the punch through type diodes has wider depletion region, right? It has a wider depletion region as compared to the non-punch through type. Okay, so naturally, if you see the condition, so NDD1 will be naturally less than NDD2, right? Because lesser doping, higher depletion region width. Okay, so that is the basic idea. So let us mark some things here. So this length is the physical width of the drift region. Okay, so this total length is the physical length of the drift region. So in a punch through type of a diode, the depletion region will span the entire width of the N minus region, like I am showing here. It will span the entire region. So the depletion layer will come to contact with the N plus layer. Now, the question is whether it will extend to the N plus layer. It might go to a little small value. It might extend to a very small value. But because this N plus region is highly doped, the depletion region will not extend a lot in the N plus region. Just how the depletion region did not extend to the P plus region, similarly the depletion region will not go to the N plus region. Even it goes, it will be a very, very small value. So we can assume that the entire depletion region is within this N minus region. So this is your W depletion region. This is your W depletion region, width of the depletion region for the punch through type of a diode. So whereas for a non-punch through type of a diode, I told you, in a non-punch through type, the width of the drift region is larger than the depletion layer width. What does it mean? It means that the depletion layer boundary does not reach to the end of the drift region. So in a diagram, how it will look like? Let me take another pen here. So in a diagram, for example, the depletion layer width might come only till this point here. The depletion layer width might only come till this point here. So this will be your W depletion layer. Okay. So I'll just write it as W depletion layer 2. And this is your W depletion layer 1 for diode number 1. Okay. And naturally this is your drift region. This is your width of the drift region. Okay. Now, what are the electric fields? This electric field concept is a little bit important. Now, usually in a PN junction, if you see the electric field of the depletion region, it is usually in the negative axis, because we are assuming that this is we are assuming towards the right side is your positive distance. So because the electric field will always exist in the opposite direction, right? That we already see. The electric field of the depletion region will be from right to left, whereas our positive direction is from left to right. So usually the electric field is drawn like this. Okay, this is the usual. In a diode, if you see, this will be the electric field. But just for aesthetic clarity, so that you understand things a little better, I will draw electric field in the positive direction. It will not affect the concept. So this is your electric field and this is your, say, distance. Okay. So if you see for a non-punch through type of a diode, okay, so your depletion region is ending at this point. The depletion layer is ending at this point. So for example, this is your maximum electric field. Okay, this area will be always your maximum electric field. So in this case, this is the boundary of the depletion region for the non-punch through type, right? This is for non-punch through type. So beyond this depletion region, there won't be electric field for the electric field will become 0 for the non-punch through type. So it will have a characteristic which looks like this. Okay, so this is for your non-punch through type. Whereas for your punch through type of diodes, if you draw the electric field, let me take another pen here. Okay, yeah. So for example, let us start with the same Emax value. So here the depletion region is extending till this point. From this point to this point, your depletion region is existing. So I have already drawn that as a dotted line. So this is your end of the depletion region for the punch through type of diode. Okay. So beyond this, the electric field will be equal to 0. So here it is decreasing very fast and this is the 0 value. But here at this particular point, at this particular axis, the electric field is not 0 for the punch through type, right? So it will gradually decrease like this. Okay. And beyond this point, you see that there is N plus layer. Okay. Beyond that point, you are having the N plus layer, and the N plus layer is so heavily doped that the depletion region will not extend to the N plus region. So here there will be a sharp drop like this. Here there will be a sharp drop. So this is the characteristic for the push through type. This is the electric field for the push through type. Now the difference you can see here is that this electric field for the punch through type. This electric field for the punch through type is much more uniform, right? It is much more uniform as compared to the non-punch through type, right? If I have used push through, just remember that it is punch through. Okay. So the punch through type of a diode has much more uniform electric field as compared to the non-punch through type. Okay. So that is the basic idea. Now there is a very interesting advantage for the punch through type of diode. Okay. There is a very important advantage for the punch through type of a diode. That is for the same breakdown voltage. So for example, you know that in basic field theory, you know that the voltage will be equal to E into X. Now this is a very crude equation. This is not the exact equation, but for the concept it is okay. Now for the same breakdown voltage, okay, so this X value will be equal to V divided by E, right? It will be V divided by E. So if VBD, we keep it as V is equal to VBD for the same breakdown voltage which has higher electric field. The higher electric field is for the punch through type. See, naturally it has a higher electric field and a uniform electric field. So as the electric field is increasing, the distance can be reduced for the same breakdown voltage, right? So for the punch through type of a diode, okay, for the punch through type of a diode which has a much more uniform type of electric field, the distance, the physical width of the drift layer can be reduced for the same breakdown voltage as compared to that of a non-punch through type. So that is the point here. For the same breakdown voltage, the punch through construction will require approximately half the drift region compared to the comparable non-punch through construction. And this is a very interesting advantage, and the explanation that I have given a very crude explanation here, but the basic idea here is that the electric field with proper doping can be almost made constant also like this. With proper doping it can be made very uniform. So naturally in this particular case, the width that is required for the drift region can be reduced for the same breakdown voltage as compared to a non-punch through type. So this is a very interesting concept here. Now some of you, if you have followed the lectures properly, you might have a doubt. So naturally the punch through diodes will have a lower doping. It has a lower doping, right? So you might have a doubt based on my previous video. When the doping is reduced, that is the doping is reduced, I already told you the conductivity will reduce. When the conductivity reduces, the resistance will increase, right? And the power loss during the conduction will increase. This I told you in the previous video. So you might think that for the punch through type of diode, due to its lower doping, okay, naturally it will have lower doping, right? It will have very high conduction loss in the forward condition. But actually that is not the case. In fact, the lower doping in the punch through doesn't mean it has higher conduction loss. Why it happens like that? Because the lower drift width, I already told you, as compared to a non-punch through type of a diode, the punch through diode requires only almost half the thickness for the same breakdown voltage. So the lower drift width, okay, the lower drift width in fact results in lower forward voltage drop. See, as the drift region will increase, so will be the forward voltage drop of the diode, because you are introducing a resistive element within the diode network, right? Naturally, it has a resistive nature that we will see in the forward characteristics. But because the lower drift width, width is small, it results in the lower forward voltage drop for the same current density as compared to non-punch through type of a diode. Okay, for the same current density, because the width is small, because of the lower drift width, it results in lower forward voltage drop. So in fact, it does not mean that lower doping for the punch through diode doesn't mean that it will have higher conduction loss. Okay, so that is the basic idea. Now I think there's a lot of concepts that we have seen today. Let us just go through them in brief. So you saw that based on the depletion width, okay, based on the depletion width and the drift layer width you can have two types of power diodes, right? Power diodes you can divide into two. One is the punch through type and the other was the non-punch through type. Okay, so in punch through type, I told you the drift region is less than the depletion region. Width of the drift region is less than the depletion region. The non-punch through type, the drift region width is greater than the depletion layer width. Okay, so what does this mean? This means that the depletion layer actually spans the entire drift region. It spans the entire drift region. And in non-punch through type, the depletion layer doesn't span the entire drift region. doesn't span the entire drift region. Okay. In fact, this is what we have seen today. In fact, if you see in power diodes, in general, you might think because of the lower doping of the N- region, you will have higher conduction loss. But there is a process which is called as conductivity modulation. There is a process called conductivity modulation which happens in the forward conduction mode. Now we are only discussing reverse conductivity. Because of this conductivity modulation in power diodes, in general, you will not have higher conduction loss. Okay, so that we will see in the forward bias condition. So in the next video, we will see the reverse characteristics, the reverse VI characteristics, and some important terms associated in the reverse bias condition of the power diodes. Okay, so I hope whatever I have explained today is clear. So till I see next video, it's me Varun signing off, and have a great day. Thank you.
Now that the video is over, please stay with me for 30 more seconds. Now the vision of this channel is to create a repository of good quality videos with crystal clear explanation regarding various topics related to electrical engineering. Now if you want to help me spread the word, please share this video with anyone interested in these topics. The second thing is that for me, education is a two-way process. Therefore, if you have any doubts or suggestions regarding any of the videos or regarding the channel, please put them in the comments below. We can have a healthy discussion, and that way we can build a strong community of electrical engineers. So that's it for today's video. So till I see you in the next time, it's me Varun signing off, and have a great day. Thank you.